Thank you. So the Big Bang is the leading theory behind the origin of the universe. According to it, the universe started a long time ago with a big explosion. All matter was but a tiny fireball, very hot, very dense, which rapidly expanded and cooled off. It took about 380,000 years for the universe to form the first elements, and also light for the first time. It took billions of years for the universe to form planets, and life, and us. With men, it came the curiosity to study our surroundings, our own existence, and our past. Since the beginning of civilizations, we've been looking at the skies, first with telescopes, nowadays with satellites. But any of these methods allow us to look so far as the early universe, because there is this barrier of darkness. Remember, light was not at that time. The early universe, however, embodies many of the key answers to understanding the universe as we know it right now and how it came to be. That's why I spend my life researching about the early universe. And the way I do it is actually to reproduce this little fireball in the laboratory, and then don't use telescopes, but rather microscopes to look into the properties of it. But how do we create a fireball? Well, it's very simple, actually. We harness the products of a highly energetic collision. In order to create such hot temperatures, we need to collide very heavy bodies, but not sumo wrestlers. Actually, we have something more heavier in our planet, which is the core of an atom, the nucleus. There are a couple of laboratories in the world able to do this. One of them is in Europe, and it's called the Large Hadron Collider. You probably have heard of it because of the recent news of the discovery of the Higgs boson. I had very lucky to study those collisions as well. The second one, it's actually here in Long Island, about 30 minutes drive south from this auditorium, and it's called the Brookhaven National Lab. This is where I currently conduct my research. Let me show you a computer animation of how one of these collisions look like. So, which we don't have for some reason. Yeah. All right. So apparently the animation is not working at the moment. It was working before, believe me. So basically, once the ions reach top speed, they collide and form this fireball. You would see that after the fireball is created, a lot of radiation would come out of the collision. Very different kinds of radiation. The rectangles represent our detectors. And each detector or each microscope, it's tuned to detect different kind of radiation. After that, we do a combined computer analysis of all the data taken and actually extract the properties of the fireball. It's very simple. It's a pity that the animation is not working now. So what have we learned so far? Well, many things, but just let me point you to 3 of them. Number 1, the matter that we created in the laboratory is very, very hot. It's actually 100,000 times hotter than the temperature that you found in the center of the sun. Actually, for those who like the Avengers, this is the neutron star where the weapon of Thor was created. So hotter than that. Second property is that it's very, very dense. It actually, if you take a tiny fraction of a drop of this matter, that tiny fraction would weigh more than the Statue of the Liberty. Number 3, and my favorite one, is that this matter has properties of that of a liquid. But not any liquid, a perfect liquid. What I mean by that is that this liquid has almost no resistance to movement. To put that in context, if I were to take and put a drop of that liquid in this auditorium, it will quickly spread over the floor, climb up the walls, climb up the ceiling, defying gravity. That's how crazy this medium is. So there are several questions still that we need to address. We are connecting the dots little by little for a better understanding of our universe. Thank you.